Derivation of the identity, $1 plus backslash tan 2a equals backslash sec 2a. Welcome, everyone. Before we dive into today's lesson, let's take a moment to reflect on what we have already achieved. In our previous lesson, we successfully derived the most fundamental identity in trigonometry. Sine squared of a plus cosine squared of a equals 1. This is a cornerstone of our study. Building on that foundation, our focus today shifts to a new objective. We are going to derive a second Pythagorean identity. This particular identity is very useful because it establishes a direct relationship between the tangent ratio of angle A and the secant ratio of angle A. Now, you might wonder why we need another identity. Well, as you progress into more advanced mathematics, you will find that this identity is absolutely essential. It serves as a powerful tool for simplifying complex trigonometric expressions and is a key step when you are solving much more difficult equations in higher-level calculus and beyond. So, let's get started with the derivation. The geometric setup. Now that we've established our goal of finding a new relationship between tangent and secant, let's set the stage for our derivation. To begin, let's visualize a standard right-angled triangle, which we'll call triangle A, B, C for our purposes. We will assume that the angle at vertex B is exactly 90 degrees. To make our calculations clear, let's label the parts of this triangle relative to the angle we are studying. Let angle A be the primary angle we are considering. The side directly across from angle A, which we call the side opposite, is side B, C, also known as the perpendicular. The side that sits next to angle A, which is the side adjacent, is side A, B, or the base. Finally, the longest side, which is opposite our right angle, is side A, C, which we refer to as the hypotenuse. Keeping these labels in mind is crucial, as we will use them in the very next step to apply the Pythagorean theorem. The Pythagorean theorem. Now that we have established our triangle and labeled our sides, identifying the base, the perpendicular, and the hypotenuse, let's apply a fundamental principle of geometry. According to the Pythagorean theorem, in any right-angled triangle, the square of the hypotenuse is always equal to the sum of the squares of the other two sides. Applying this specifically to our triangle, we can write the relationship as a b squared plus bc squared equals a c squared. Keep this equation in mind, because in the next step, we are going to manipulate it to reveal our target identity. Step-by-step derivation. Now that we have established our right-angled triangle and stated the Pythagorean theorem, where side ob squared plus side bc squared equals side ac squared, we need to figure out how to transform this equation into our target identity. Our goal is to derive an identity that specifically involves the tangent and secant ratios. If you look back at our definitions, you'll recall that tangent of A is equal to BC over ob, and secant of A is equal to AC over ob. Notice a common pattern here. Both of these ratios have the side ob, which is our base, in the denominator. So, to bring these ratios into our Pythagorean equation, we need to manipulate the terms so that ob appears in the denominator of each part. The most effective way to do this is to divide every single term in our equation by ob squared. Let's see how this looks in the next step. Step 1. Divide the equation. Now that we have identified our goal, which is to introduce the tangent and secant ratios into our equation, let's move on to the first actual step of our derivation. As I mentioned on the previous slide, both tangent and secant share the same denominator, which is the base, ob. Therefore, to transform our Pythagorean theorem, we are going to divide every single term in the equation by ob squared. If you look at the screen, you'll see the equation rewritten this way. Ob squared divided by ob squared plus bc squared divided by ob squared equals ac squared divided by ob squared. This algebraic manipulation is the key that will allow us to simplify the expression into trigonometric ratios in the next step. Step 2. Simplify the terms. Now that we have divided every term in our Pythagorean equation by the square of the base, as we saw in the previous slide, let's move on to step 2, where we simplify these terms. First, look at the term on the left, ob squared divided by ob squared. Since any non-zero value divided by itself is simply 1, this term simplifies to 1. Next, let's look at the second term, which is bc squared divided by ob squared. Using the laws of exponents, we can group these under a single power, rewriting this as the ratio of bc to ob, all raised to the power of 2. Finally, we apply the same logic to the third term on the right side of the equation. ac squared divided by ob squared can also be rewritten as the ratio of ac to ob squared. By simplifying the equation this way, we are setting ourselves up perfectly for the next step, where we will substitute these ratios with their corresponding trigonometric functions. Step 3. Substitute trigonometric ratios. Now that we have simplified each term individually in the previous step, let's bring them all back together. Looking at our equation, it has now transformed into 1 plus the quantity bc over ob, all squared, equals the quantity ac over ob, all squared. Now we move on to step 3, which is to substitute our trigonometric ratios. If you recall our fundamental definitions from earlier in the lesson, we know that tangent of A is equal to BC over ob, and secant of A is equal to AC over ob. Because our equation is currently written in terms of these side lengths, we can now perform the substitution. By replacing the BC over ob part with tangent of A, and replacing the AC over ob part with secant of A, our equation becomes 1 plus tangent of a squared equals secant of a squared. This brings us much closer to our final identity. Step 4. Final notation. Now that we have successfully substituted our trigonometric ratios into the equation, we move to our final step. Step 4, which is the final notation. You'll notice in the previous slide that we had the terms written as tangent of a all squared and secant of a all squared. While this is mathematically correct, it's a bit cumbersome to write out during long proofs. In trigonometry, we use a much cleaner shorthand. We write the tangent of a squared simply as tan squared of A, and we write the secant of a squared as sec squared of A. By applying this standard notation, we arrive at our completed, beautiful identity. 1 plus tan squared of A equals sec squared of A. This is the final form of the identity we set out to derive today. Domain of validity. As we have seen in our derivation, this identity is valid for all values of angle A, starting from 0 degrees up to, but not including, 90 degrees. It is very important to note that the identity is not defined when angle A equals exactly 90 degrees. Let's think back to our geometric setup in slide 2. Remember, both tangent A and secant A are ratios that involve dividing by the length of the base, ob. If the angle A reaches 90 degrees, the base, ob, effectively shrinks to 0. As you know, division by 0 is undefined in mathematics. Therefore, the ratios BC over ob and AC over ob become undefined, which means our identity cannot be applied at that specific point. Now, before we move on to see how we can apply this in a real-world scenario, we must discuss the domain of validity. This is a crucial step in mathematics, knowing exactly where our formulas actually work. Real-world application example. Now that we have mathematically proven the identity, let's step away from the abstract algebra and see how this actually applies to a real-world scenario. Imagine you have a ladder leaning against a vertical wall. If you look at the setup from the side, the ladder, the wall, and the ground form a perfect right-angled triangle, just like the triangle ABC we used in our derivation. In this scenario, the distance from the foot of the ladder to the base of the wall represents our base, which we labeled as ob. The height that the ladder reaches up the wall is our perpendicular side, or BC. And finally, the actual length of the ladder itself is our hypotenuse, which is AC. Now, here is where the power of trigonometry comes in. Suppose an engineer is inspecting this setup and knows the angle, which we'll call angle A, that the ladder makes with the ground. Using the identity we just derived, 1 plus tangent squared of A equals secant squared of A, the engineer can relate the slope of the ladder. which is the tangent of A, to the ratio of the latter's length relative to its distance from the wall, which is the secant of A. The beauty of this is that they can establish this relationship using only the angle, without ever needing to physically pull out a tape measure to find the actual lengths of the sides. Key takeaways. First, it is crucial to remember the logic we used to reach our goal. We didn't just pull this formula out of thin air. We derived the identity 1 plus tangent squared of A equals secant squared of A by taking the Pythagorean Theorem, which is a b squared plus bc squared equals a c squared, and dividing every single term by the square of the base, which is a b squared. This algebraic manipulation is what allowed us to transform side lengths into trigonometric ratios. Second, keep in mind the practical utility of this formula. This identity is a powerful tool in your mathematical toolkit because it allows us to seamlessly switch between tangent A and secant A when we are working through complex mathematical proofs or simplifying expressions. Finally, always be mindful of the constraints. As we discussed briefly in the previous slide, this identity is only valid within the domain where the ratios are defined, specifically for the range where A is greater than or equal to 0 degrees, but strictly less than 90 degrees. All right, let's wrap up our lesson by reviewing the key takeaways from today's derivation. Now, before we finish, let's look at some common pitfalls to avoid so you don't lose marks on your exams. Common mistakes to avoid. First, let's talk about confusing the ratios. It is very easy to mix up our Pythagorean identities when you are in the middle of a complex problem. You might accidentally swap this identity with one that looks similar, specifically, 1 plus cotangent squared of A equals cosecant squared of A to keep them straight. Just remember the pairings. Tangent is always paired with secant, and cotangent is always paired with cosecant. Second, please be careful with your notation regarding squaring. A common mistake is misinterpreting what the exponent means. You must ensure you understand that tangent squared of A is simply a shorthand way of writing tangent of A, all squared. It does not mean you should square the angle itself, as in tangent of a squared. The operation applies to the entire ratio, not the argument. Finally, do not ignore the domain of validity, which we discussed briefly in the previous slide. It is crucial to remember that this identity is undefined at 90 degrees. If you are solving trigonometric equations and you forget that the identity fails at 90 degrees, you might end up with an invalid solution. Always keep an eye on those constraints. Now, before we conclude our lesson, I want to touch upon some common pitfalls that students often encounter when working with this identity. Being aware of these will help you avoid unnecessary errors in your exams. With these points in mind, you should be well equipped to use this identity confidently in your mathematical proofs.